Alright, so this is preparation for the experiment that students did in class today. First we talked about different musical instruments, the first of which is a string instrument where you have a wave that is a standing wave on an instrument or a geometry that's a string fixed at both ends. And we've just designated the length of the string as L. And the very first standing wave that can be produced on a string like this is one where, as you can see in this picture, there's a note at each end because it's fixed, and then therefore just one antinote in the middle. And you can picture that that would be half of a wavelength. If I draw a picture of an entire wavelength and then highlight the section that we've shown here, you can see that this first standing wave, which we call the fundamental frequency, is half of a wavelength long. But then that's not the only standing wave that can be produced on this geometry. It's just the first one. And so the next one is going to have, again, nodes at both ends, but it's going to have another node in the middle, resulting in two antinodes. And this is what we're going to call the first harmonic, which is a step up from the previous standing wave. And you can imagine then that the length of the string there is equal to one wavelength. And I'm just going to rewrite these fractions in terms of fourths, and you'll see why later. But for the fundamental frequency for a string at both ends, it's then 2/4 of the wavelength, and the first harmonic will be one wavelength, or 4/4 of the wavelength. So then you can imagine the next one is going to have an additional node in the middle, so that now we have the two nodes at the end, we have two nodes in the middle for a total of 4, and of course 3 subsequent antinodes, and we're going to call this the second harmonic. And you can picture there that that means that the length is 3/2 of a wavelength, or we could write that as 6/4. The next one will have another node, resulting in being 2 wavelengths long, or 8/4. And of course we call that the third harmonic. Now, these are for stringed instruments, or any standing wave on a string that's fixed at both ends. We might also imagine an instrument that is a tube open at one end and closed at the other. And the very first time we're going to get a standing wave on that is a situation like this, where the closed end has to be a node because the medium won't be free to move there, and then the open end is going to be an antinode. And so the very first standing wave will be produced in this configuration, which you can imagine is 1/4 of a wavelength. And again, here the entire wave, and the part that's shown by this geometry is highlighted in blue. And so the fundamental frequency for a tube open at one end is 1/4 of a wavelength. The next one then is going to, still has to have a node at one end and an antinode at the other end, but it'll have another node in between. And so now we have an antinode and a node in between, resulting in this, which is the first harmonic. And again, looking at our picture, you can imagine then that is 3/4 of a wavelength. The next harmonic then will have an additional node in between, an additional antinode in between. We'll call that the second harmonic, and as you can see, that's going to be 1 1/4, or 5/4 of a wavelength, and so on and so forth. Now, hopefully now you can see why I chose to rewrite the fractions of the string fixed at both ends in terms of fourths, because they went up on all the even fourths. It started at 2/4 and 4/4 and 6/4 and 8/4, whereas the fixed at one end, open at the other, is going to go up by odd fourths. It's going to start at 1/4 and then go to 3/4 and 5/4 and 7/4 and so on. Now, I don't want you to memorize that shortcut. I want you to be able to produce it the same way we're doing here, by rebuilding each subsequent wave, but it's good to know the shortcut as well. All right, so then the last thing we need to examine before determining the speed of sound in our experiment is the definition, or excuse me, the equation that relates wave speed to these quantities. You remember that any speed is a distance over a time, and so I want us to think about a specific distance, namely a wavelength, and the time that it takes the wave to travel one wavelength, of course, is the specific time that we have defined as being the period, or the time required to complete one cycle. And so I can substitute that for distance over time, wavelength over period, and then you also remember that, or I can rewrite this algebraically as, I can just separate that fraction. It's lambda times 1 over period. It's just rewriting the exact same thing, but that helps me to identify 1 over period. You'll recall that 1 over period is, of course, frequency. And so therefore, what we've determined is that the wave speed is equal to the wavelength times the frequency. And so that's what you're going to use in lab. You're going to determine, you're going to use the different frequency tuning forks. You've got a geometry of a tube that's closed at one end and open at the other. And therefore the very first standing wave you can produce, the so-called fundamental frequency, will be 1/4 of the length of the wavelength. And so using that, you can determine for each frequency what the wavelength of the wave is. And then, of course, we'll graph some form of those two variables in order to determine the speed of sound. And I'm going to let you wrestle with exactly what we need to do, what manipulation we need to do to our variables in order to get a linear graph to determine the speed of sound.